All right, let's talk about something you've definitely seen, but maybe never really thought about. How does a hot air balloon float? Or why does a tire look kind of flat on a really cold morning? Well, the answer to both is this really cool fundamental principle of science called Charles's Law, and we're going to break it down. You've totally seen this, right? You have a perfectly good party balloon, you take it outside on a chilly day, and suddenly it looks sad, deflated. But what's going on? It's not a leak. The answer is actually hiding in the invisible world of physics. So, that shrinking balloon, it's the perfect real-world example of a fascinating scientific law in action. It's not magic at all, it's just pure science. And the rule that explains it all is called Charles's Law. It's named after Jacques Charles, who figured this all out over 200 years ago. And what he discovered is this super direct, super predictable link between two things we deal with all the time: temperature and volume. Okay, so here's the official definition. Charles's law says that when the temperature of a gas goes up, its volume also goes up, and, you guessed it, when the temperature goes down, its volume goes down. The one little catch? This all works as long as the pressure stays the same. I mean, look at this. It doesn't get much simpler, right? Temperature and volume are basically a team. One goes up, the other goes up. One goes down, the other one follows right behind it. They're totally locked in step. But why does this happen? I mean, really, what's going on? To get that, we need to zoom in, like way in, and look at the tiny little particles that make up the gas. It's all about energy and motion, a kind of microscopic dance. So when you heat a gas, you're pretty much giving every single particle a shot of espresso. Seriously, they absorb all that heat energy and just start zooming around, bouncing off each other, hitting the walls of their container. It's chaos. And to make room for all that new energy, they have to spread out. And boom, the volume gets bigger. And, of course, the exact opposite happens when you cool things down. You're taking energy away, the particles get sluggish, they slow down, they don't collide as much, they just kind of huddle closer together, which means they take up way less space. And that, right there, is why our balloon shrinks in the cold. Here's a really great way to picture this. Just imagine a bunch of tiny marbles bouncing around inside a box. If you shake that box like crazy, you're adding energy, those marbles are going to fly all over the place. They're going to need a much bigger box, right? But if you barely shake it, they'll just settle down at the bottom and take up a lot less space. Okay, so now that we get the science, let's look at how this whole thing plays out in the world all around us. Because once you know what to look for, I promise you are going to start seeing Charles's Law everywhere. So let's go back to our original mystery, the balloon. You leave it in a hot car and it expands, right? Sometimes it even pops. That's because the air particles inside are super energized and they're pushing outwards. But in the cold, those same particles just slow down, huddle together, and the balloon looks deflated. Mystery solved. This happens with your car tires too. You know how the tire pressure warning light sometimes comes on during the first really cold day of the year? That's Charles's Law. The air inside the tires has cooled down and contracted. But then, after you drive for a little while, the friction from the road heats the air back up and it expands again. And get this, it even happens inside our own bodies. When you're outside and you take a deep breath of that crisp, cold winter air, that air is actually pretty dense and compact. But the second it hits your warm lungs, which are about 98.6 degrees, it instantly expands. How cool is that? Charles's Law is a part of every single breath you take. Now, like pretty much any law in science, this one has some fine print. It's a beautifully simple idea, but it really only works under a couple of specific conditions. There are two big rules to the game here. First, the pressure has to stay constant. If you're squeezing the container, all bets are off. And second, the amount of gas can't change. You can't be adding more air or letting any out. It has to be what we call a closed system. Now, for anybody who likes the math behind it, here's the formula. V is volume and T is temperature. It's just a simple way of saying that the ratio between the starting volume and temperature is going to be the same as the ratio between the final volume and temperature. But there's one detail here that is absolutely critical if you're going to do the math. You can't use Celsius or Fahrenheit. The temperature has to be in Kelvin. And you might be wondering why. Well, it's because the Kelvin scale starts at what's called absolute zero, the point where particles theoretically stop moving entirely. That makes it a true measure of energy, and you need that for the ratio to work perfectly. So after all that, the particles, the examples, the formulas,
It all comes back to this one simple, powerful idea. For a gas, as long as the pressure is constant, temperature and volume are a team. They rise together and they fall together. Always.
So I'll leave you with this little thought experiment based on everything we just talked about. If you double a gas's temperature, using the Kelvin scale, of course, what do you think happens to its volume? The answer is simple and really elegant, just like the law itself.